Hi there, welcome to my presentation. My name is James Valence. My research is a comparison between two types of models that are trained to perform super resolution. Firstly, let's talk about what super resolution is. Super resolution is the act of realistically upscaling or increasing the resolution of an otherwise low resolution or compressed image. Super resolution models are used widely today. Some examples of such are super resolving medical imagery for easier diagnoses, super resolving astronomical images, and most notably, super resolution has been added as a feature in many newer cell phone cameras. These cameras perform super resolution on digitally zoomed in photos, because digitally zoomed in photographs have a tendency to become more rasterized the greater level of digital zoom. Super resolution is performed by generative models, since by nature super resolution is a problem of filling in the gaps between pixels where image information is missing. In the past, generative adversarial networks have dominated the field in both abundance and output quality. However, recently, since about 2020, there has been an increase in popularity in implicit neural representation models. These models have been applied to many other image-based problems that GANs have excelled at and have performed comparably. GANs are trained on what we call explicit features. This is all the properties of an image that are available to a network in all of its pixel values. For example, the RGB values are explicit features. The RGB values can be converted to HSV values. Since this is such a trivial conversion, these are also explicit values. Thus, this includes any other property that can be found from the image in its default representation. Implicit neural representation models do not use the explicit features of an image. Rather, they convert the explicit representation into an implicit function that represents the image continuously. This type of model was popularized in 2018 in a paper called Neural Scene Representation and Rendering, which aimed to represent a scene implicitly through images from multiple viewpoints. Since this function representing an image is continuous, it can be sampled at an arbitrary rate to yield an output image of any resolution. When performing super resolution in this way, we sample this continuous function to get information about a greater number of pixels than we had in the input. Once these new points are decoded, the result is an image of greater resolution than the input. Explicit models learn to produce output images that best minimize or maximize a particular loss function, whereas implicit models learn how to convert an image to this continuous domain in such a way that when decoded produces a legible image. In our research, we particularly investigate the Laplacian super-resolution network and the Laplacian GAN, as well as the local implicit image function model. The Laplacian GAN is a GAN that learns explicit features, and the LIIF model learns to convert images to a continuous domain. The aim of our research is primarily to compare the performance of the LAP-GAN to the LIIF model when trained on comparable training set and learning parameters. Secondarily, we compare the effects of different loss functions within the LAP-GAN so that our comparison takes into account a potential bad loss function. The LAP-GAN is a GAN based on the Laplacian pyramid. I won't go into too much detail explaining the architecture of this model, but essentially the network is made up of multiple subnetworks that we will denote as layers for the sake of this explanation. Each layer of the LAP-GAN is a separate GAN that is trained to super-resolve its input by a factor of 2. The first layer takes in low-resolution input, super-resolves it, and the output acts as the input to the next layer. In this research, we compare how well each model super-resolves images by a factor of 4. Thus, our model will have 2 layers. We consider 2 loss functions and variations between them in our LAP-GAN models. The first is the adversarial loss, that is determined by how well the discriminator in the LAP-GAN is able to perform in discriminating between generated images and ground truth images. The second is the minimization of the mean square error. Technically, we use a regularized form of the mean square error called the Charbonnier loss to prevent mode collapse, but for the sake of this report, we will denote it as the mean square error from now on. The local implicit image function model aims to convert multiple local areas of an image into an implicit representation. This means that the image is split into many continuous functions. When sampling a new pixel, the predictions of each new pixel information from each neighborhood is merged based on the normalized confidences of each neighborhood with regard to that pixel location. This confidence is based off of distance. Firstly, let's go over the configurations of the LAP-GAN we trained for our comparisons. Firstly, we trained a Laplacian super-resolution network, which does not consider adversarial loss when training, and thus it is not a GAN. This model solely aims to minimize mean square error of the output it produces. We call this Model 1. Secondly, we train a lap GAN that aims to minimize adversarial loss in the first layer and mean squared error in the second layer. So this model is essentially a GAN that outputs into a lap SRN. We call it Model 2. Our Model 3 is the opposite, where it is trained to minimize mean squared error on the first layer and adversarial loss on the second. The fourth model was trained to minimize adversarial loss everywhere. The final model, which is the model that was proposed in the original LapGAN paper, minimizes both mean squared error and adversarial loss on both layers. All LapGAN models and the LIIF model have been trained on 800 training images with 200 validation images. The outputs of the models have been evaluated both quantitatively and qualitatively. The quantitative measures were done simply by means of calculating some of the structural metrics common in evaluating super-resolution models. But this doesn't necessarily ensure that the output is good. What is a good output when it comes to super-resolution? A good super-resolved image is visually convincing to the individuals who view it. Unfortunately, there are no quantitative measures to determine this, so we sent out a survey to anonymous participants who picked out the most visually convincing outputs based on their own intuition. The results are as follows. The quantitative results show that the LIIF model outperformed all other models with Model 1 as a close second. The qualitative results show that the LIIF model, again, outperformed other models, but this time crushingly. The LIIF model outputs received 145 votes for most visually convincing, and the second place only got 23. We had originally hypothesized that Model 5 would outperform the LIIF model, but this hypothesis was disproven. One thing to note is that the structural metrics were a decent indicator to which models would perform better than others with respect to visual convincingness, but not to the degree at which they would win by. Here is a sample of some of the zoomed-in output images from each model. Immediately you can see Model's one output is blurry. This is characteristic of models trained solely on mean squared error. Model 3's output has an obvious checkerboard artifact that is indicative of transposed convolution, which is present in each LapGAN layer. Models 2, 4, and 5 look waxy, which can be off-putting to human participants. This might be mitigated by further training. The LIIF model looks slightly blurrier than the GANs, but it has sharper lines and clearer shapes. This is why we believe it won the contest of most visually convincing. In conclusion, our hypothesis that one of our explicit models would outperform the LIIF model has been disproven. This shows great promise in the LIIF model and implicit neural representation models as a whole. However, for one to make the statement that INR models are a better choice than explicit models for super-resolution, much more comparison needs to be done with different models and different training parameters. Super-resolution models go out of date very quickly, and new methods pop up all the time. With the increase in popularity of these INR models, we don't think this will slow down anytime soon. Thank you for watching my presentation. I hope it was interesting for you.